Very good morning, everyone. In the day 6 of Faculty Development Program on Smart Health Innovation, Integrating Imaging, Sensor and Biomaterials. Today, we have 4 eminent speakers who will deliver their talk, and we are highly honored and privileged to have Professor Kunal Pal sir, who has joined this meeting, and we are very thankful that he has accepted our invitation to deliver the keynote talk. Dr. Kunal Pal sir has obtained his bachelor degree in pharmacy from the College of Pharmacy, New Delhi, India. He pursued further studies, completing his master in engineering degree in biomedical engineering at Jadavpur University, Kolkata, and earning a PhD in material science from IIT Kharagpur. Following this, Dr. Pal served as a postdoctoral fellow at Ryerson University in Canada, broadening his global perspective. In 2009, Dr. Pal began his professional journey as an assistant professor in the Department of Biotechnology and Medical Engineering at National Institute of Technology, Rourkela. His research primarily focused on biomaterial, drug delivery mechanism, food science, and innovative food design. Dr. Pal also possesses expertise in biomedical instrumentation and signal processing, showcasing his multidisciplinary approach in the biodomain. His academic integrity is evident through his extensive publication record that include more than 300 Scopus Index research article and 45 paper having a high H index. Notably, he has been recognized in Stanford University top 2% scientist list for the consecutive year 2022, 2023 and 2024. Dr. Pal has established research collaboration with several labs within the outside India, including the Indian Institute of Technology, Jodhpur, Seoul National University, South Korea, King Saud University, Saudi Arabia, University of Philippines, Los Banos. As the principal investigator, Dr. Pal has secured 9 sponsored research grants in India. His recent achievement including securing a bilateral grant titled Development of Composite Optic Device employing an artificial intelligence algorithm for evaluating the shelf life of raw agricultural product from the Department of Science and Technology, International Cooperation Division, Government of India. In collaboration with the Department of Science and Technology, Philippines. Additionally, Dr. Pal obtained another significant grant titled Developing an Artificial Intelligence-Enabled Multispectral Reflectance Photography Device for the prediction of shelf life of bakery product from the Science and Engineering Research Broadcare Research Grant, Government of India. The title of presentation will be the development of multifunctional optical device for the process monitoring application. So we are highly fortunate to invite our keynote speaker, Dr. Kunal Pal sir, at this FDP session. We thank you, sir, and stage is yours, sir.
So it was truly an honor that you accepted our invitation. So the stage is yours, sir.
Yeah, thank you, no, Professor Vanesh, and thank you other faculty members and the organizing committee who have been associated with this workshop. It's truly an honor to give a presentation and share what we are doing at our lab at NIT Rourkela with you guys. Okay, so I would especially like to thank Dr. Uvanesh for inviting me. So he gave me a call and he was telling that there is no fund for us. No, that's not a problem. As a researcher, it is always our lookout how we can share our knowledge, and I am happy to share my knowledge with the young minds, because what I believe is that uh, sharing when if I share the knowledge, so the knowledge will be percolated to a mass, and maybe from a single word or single say a line what I speak, it may open up a new research area domain for the listeners. Okay, I would give my uh, one example. What happened is that one of my PhD students, I asked him. In fact, he was the classmate of Dr. Vanesh, and I asked him to visit 4 or 5 workshops across the India. He also went abroad for one conference. So from those 4 or 5 workshops, out from 2 or 3, he got single word from those workshops. Okay, it was all say 4 or 5 days workshop, but he got some keywords which are the buzzwords, and that on that topic people were working. So using those 3 or 4 keywords, he shaped his PhD career, and he is now doing well. He is running one company. So he has started his entrepreneurship business. So like that, there are several other examples where I always ask students to to go to various workshops and listen to what others are speaking, what others are doing, because the what say whatever I am doing, maybe that facility is present to for you also, but you are not able to extract the information from there. When I speak to you, and when I will demonstrating my results, it might so happen that you will get an idea that okay, we can represent this data in that way also. Okay, so it opens up a broad perspective in the minds of the listeners or the researchers. Okay, so with this short talk, I will start my this presentation. Okay, share. So is my screen visible to you?
Yes, sir. Yes, sir. Yes, sir.
Okay. This is the problem. Let me- Hmm, Okay. Anyhow, so good evening, everyone. So good morning, everyone. So what I will do is that I will start with my talk, and this talk would be uh, an interactive one. So if any one of you are having any issues, or you want to know anything from any specific slide, please don't hesitate to stop me, and then we can discuss about that principle or whatever doubts you are having. Okay, so today I'll be discussing about the development of multifunctional optical device for process monitoring applications. I'm sorry, this band, it is not going, so I'm not finding the way to hide it, and it is not going out of the screen also. Anyway, might be uh, this Zoom, they have changed their settings somewhat, because previously we could hide this band. Okay, anyhow, so as the organizing team, they have already introduced me. So I am Professor Kunal Pal, and I am working at the Department of Biotechnology and Medical Engineering at NIT Rourkela. Okay, so as you can see, you must have heard from the introduction. I basically work on many areas, including drug delivery, including biomedical, including food technology. Okay, so what is the common thing that binds my research? The common thing is the human health. Whether it is drug delivery, whether it is food science, whether it is biomedical engineering, in all the things you will see in somehow or somewhat these areas they affect the health of a human population. Okay, when we talk about the food, we need to maintain a certain degree of food quality and safety. Okay, because across the globe what happens is that every year nearly 4.2 lakhs of people they die due to foodborne illness. Okay, and uh, apart from this, there is a huge number of population who undergo morbidity, not mortality. Mortality means the death, and what I mean to say, no, morbidity, where people suffer, and when people are suffering due to some illness, it also affects the GDP of the country. Okay, so due to this reason, it becomes customary to analyze the quality aspects and the food safety aspects of the food. These are some of the common quality aspects and the safety aspects that are being monitored in day-to-day life by the food regulators. Okay, so among these, the optical devices that we developed at our lab, they are more what you call they help us in analyzing these highlighted areas. That means the appearance of the food, the processing techniques of the food. Then it can help us in food fraud and detection. It can help us in analyzing the microbial biological safety of a food product, right? So apart from this, if you look into the appearance, through the appearance we can guess the freshness, we can guess the texture. And when we talk about this packaging, through packaging, what is the major, one of the major what you call this application of the packaging system, it is to stop the microbial growth. Okay, so if you see, most of the things are interrelated. So using that optical device, if you see, we are able to analyze a large number of the quality and the safety aspects related to the food. Okay, and for that person, for that reason, what we have done is that we have taken 4 parameters that we wanted to study across this whole span of quality and the safety aspects. Okay, so when we talk about this food inspection, so we can do the food inspection by various methods like chromatography, then spectrophotometry, microbiological testing, hyperspectral imaging, NIR spectroscopy, and SERS. SERS means surface enhanced Raman spectroscopy. Okay, so these are the common techniques. But if you look, most of these analytical techniques that we propose, they are either very costly or the sample preparation is very what you call tedious. Okay, similarly if you look into the microbial biological testing, so we have to do the microbial test for at least 24 hours to get some meaningful results. So in that regard, what people are suggesting is that to reduce the time of analysis, they are going for the spectrophotometric based testing. It may be spectrophotometry, it may be hyperspectral imaging, it may be NIR spectroscopy, or it may be ACRS. Okay, so people are trying to analyze these things to reduce the time that is needed to do the microbial biological testing. But the problem is that if you look into these systems, including the spectrophotometry, which is the cheapest among all these analytical tools, so what happens is that their cost is very very high. If you look into the spectrophotometry, it would cost, say, the double beam spectrophotometry. It costs in today's date, it costs around 5 lakhs. Okay, Indian rupees. Okay, So hyperspectral imaging, it costs around 50 lakhs. Okay, NIR spectroscopy, it costs around 30 to 40 lakhs. Okay, Raman spectroscopy, it costs around 70 lakhs. So our main aim was to determine whether we can make a low cost solution which can help us in analyzing the food products, and at the same time it will not be compromising with the quality of the analysis. Okay, so as I already told you, uh, this thing. So as I already told you, these systems, they also have some limitations. So what are the limitations? The limitations include most of these analyses, they are destructive in nature. Okay, so that means if you are having a food product, you have to cut it or do some sample preparation, and you will not get back the original sample. Okay, so they are destructive in nature. And if you want to randomly check some samples whether it is contaminated or whether it is safe for consumption, and if you try to destroy mm, some products, it is a loss to the manufacturer or the retailer. So you don't want that to happen. Okay, the second thing is that it's extensive sample preparation methods. Then it is labor intensive. Okay, because you have to prepare the sample and all these things. It can be time consuming. You need skilled personnel to go for the analysis. And as I already told you, most of the techniques, they are highly costly. Okay, so saying this, what are the non-destructive methods? Because if we can design one analytical method that is non-destructive in nature, so what it can do is that it can save a lot of money, not only for the industrial setups, but also for the uh, retailers who are selling the products. Okay, because we will not be destroying their food products, and that will be spared and they can sell it. So among these, some of the common things are optical imaging. Okay, second is visible spectroscopy based analysis. Then uh, next is infrared spectroscopy, and lastly it may be a mass spectrometry. In the mass spectrometry, we have to have some amount of sample which needs to be injected. So we are not uh, basically, it is not completely non-destructive, but since we are taking only a small amount, say in the milligrams, so we are taking the samples, and hence it is often classified under non-destructive methods. Okay, so what are the advantages of these spectroscopic techniques for the food safety analysis or food safety prediction? Okay, so first one is, it is having a rapid testing, then non-destructive, and lastly the environment friendly uh, method of analysis. Okay, challenges in deployment: complex instrumentation. Okay, data acquisition and analysis, it can we have to use algorithms, and we need to generate large data sets. And lastly, scaling for industrial use. As I told you, if I ask a small MSME industry to integrate a 70 lakh instrument for the analysis of the food products, they will not use it. Okay, so that is the main problem. Okay, then coming to the recent advancements with the development in the field of sensor integration, sorry, in the field of sensor integration, data processing, and real-time monitoring systems, it is now possible to develop or implement these complex systems in the food industries, and that too at a low cost. Okay, so what are the research gap? The research gap includes the lack of multiple parameters, monitoring of the multiple parameters simultaneously. Okay, then miniaturization and portability. So we need to miniaturize the product so that they can be applied for on-site application. Then next is integration of AI driven analysis, because when we integrate this AI driven analysis, it increases the chances of positive prediction, and it reduces the chances of false prediction. Okay, and lastly, cost effective when we integrate these AI driven systems to with the low cost systems, it can give us cost effective solutions. Okay, so herein what solutions we are providing, what we try to do is that we try to take the color information, spectral information and hyperspectral information, and we try to develop an instrument which is capable of collecting all these three information, and then we try to integrate our AI models with that, so that we should be able to get uh, get automated analysis and detection of the sample. Okay, so for that purpose, we went for these 5 objectives. So initially we developed a standalone multimode colorimeter for process monitoring applications. So then what we did is that upgradation of the colorimeter to spectrometer, okay, for non-invasive foliage monitoring using machine learning models. Okay, so what we have done is that we have taken the spectrometer, we have converted this colorimeter to the spectrometer, and it is quite interesting topic, because when we talk about the colorimeter, we use imaging sensors where we are having only RGB planes. Okay, so when we talk about the spectrum, we are having in the visible spectrum, we are having 400 to 800 nanometer wavelength. Okay, so out of this we are having only three wavelengths. Okay, red is at around say 780, green is somewhere around 650, and in blue region it is around 400 or 450, wherever you want to take. So out of this full wavelength spectrum, in RGB cameras we are having only three wavelengths. Okay, we are having only three wavelengths. So from there, how we got the full wavelength spectrum, I will be discussing with you with that. Okay, then after we developed this spectrometer, we developed deep learning framework using the digital images that were captured using the colorimeter cum spectrometer for non-invasive foliage monitoring. Okay, then we upgraded this spectrometer into a hyperspectral imaging system. Okay, into a hyperspectral imaging system. Okay, and then lastly we did the integration of optimized AI models into a unified platform. Okay, so that means we took the uh, this colorimeter information, we took this deep learning information from the images that we captured, so simple image processing. Then we used this hyperspectral images, that means the images at the different wavelengths for the detection, and then we developed an integrated platform over there. Okay, so this is the total workflow that was carried out. Okay, I am not going into the detail, I have already told you in brief, but we are expecting in this presentation. So first one is the development of a standalone multimode colorimeter. So we developed a device. So this is the device over here. So we have an imaging sensor inside it, and this is the sample that we wanted to analyze. And herein we were not only analyze the color parameters, but we are also looking into the uh, this temperature based crystallization process, and we are monitoring the uh, process from there. And then we if you see over here, we are getting information L star and temperature, which is analog to the heat flow and the temperature that we get from the DSC machines. Okay, so which is highly costly in today's date. It would cost approximately 30 lakh rupees. Okay, so then we tried to correlate both this data, and we wanted to find out whether our system is capable of identifying critical thermal events. Okay, and that too using a very low cost solution. Okay, because if you see over here, if I ask many of you that can you buy a 30 lakh equipment, it will be very difficult for you to procure a 30 lakh equipment using the government funding. And also the government funding is very it goes through a very hard selection process, and not many of the researchers, they get the funding to procure high cost equipments. Okay, so lastly, what we did, once we analyzed this and once we saw, yeah, our device can be used, we tested butter sample to analyze the crystallization process uh, in the molten butter. Okay, so this is the device. If you see, we are having a thermal sensor. Okay, over this is a spacer which will guide the light, and it will also help us in capturing the images. Okay, so here is the sample platform. So it is a sliding platform. Okay, and this is the software that we developed. Okay, so the device was made IoT enabled, so that if I want to incorporate this, suppose I want to analyze the crystallization process in a controlled environment, I can put it into the controlled chamber, and through the IoT I can get the result uh, outside, and I can analyze the results from outside without disturbing the sample. Okay, so how this system works? So first we have, so these are the images from the original system. So if you see, we are having a black card first, and then we are having this white placard. So first we have to do black and white calibration. So first we need to do the black calibration. We will put a black object, standard object, then we will take the reading from the region of interest. We do not take all the image, we just take a small part. Okay, so we take the region of interest and select the region of interest, and from there we calibrate the image for the back calibration. Then we go for the sensor calibration for the white calibration. Okay, and once it is completed, once the calibration of the sensor is done, then we have uh, two types of this what you call two types of modes in which the device can be operated. The first one is the quality testing mode, and the second one is the process monitoring mode. In the quality testing mode, you can bring different samples and you can analyze the samples one by one. Okay, and in the process monitoring mode, once you start the analysis, it will record the results for a particular period of time as per the details that you have given to the GUI. Okay, in this B section, if you see, we have put a different colored placard. After the calibration was done, we selected the quality testing mode. This placard was put in, and then we tested the sample, and here we get the perceived color. Now if you see, both the actual placard and the perceived color, they are having the similar color information, and all the color parameters in the RGB plane, CMY plane, HSI plane, and CIE lab plane, they have been computed for this perceived color. Okay, now this color informations can be used by the paint industry, by the textile industry, by the say food industry in analyzing or characterizing the samples. Okay, then coming to the process monitoring mode. In the process monitoring mode, see, we are having a specific uh, thing over here. So in the process monitoring mode, we have to give the process time for how long the instrument should run. The second is time interval, at what interval the instrument should take the reading. And since we were interested in capturing or capturing the thermal event based readings, we had a start temperature. So it is the temperature after achieving which the device will start recording the data. Okay, so from here, if you see, we got the intensity versus the time plot, but once we get the data, we can extract the time versus color parameters and data. Okay, So initially what we did is that we once we developed the device, we tried to analyze the device whether it is performing well or not. So we generated some color placards having definite color parameters, okay, and this is the image of those placards, okay, those colors. Then we acquired the data from a commercial device and from our developed device, okay. So what happens is that if you see delta is nothing but the difference in the color information between the original placard and the color information obtained from the respective devices, okay. So over here if you see in the delta E value, in all of our cases it was much lower than the commercial device, okay. If you see in the first case, in the case of red, our device gave a delta E of 3.33, whereas in the case of the commercial device it was 48.32. Similarly, in for the yellow, for the commercial device it was 16.58, okay. Now as per the literature, what happens is that if the delta E it is lesser than 5, then you will not be able to analyze whether there is a visual change or not, okay. So any values having delta E or any placards having delta E greater than less than 5, we will not be able to perceive that change visually, and up to 10 delta value it is quite accepted in the food industry, okay. So in most of our cases if you see, uh, in many cases it was less than 5 and in some cases it was within the limit of 10, okay. So that's why if you see the device that we developed, it can be regarded as that it can be used for the product quality analysis purpose, okay. So then as I told you, we went for the analysis of process monitoring analysis of the these oleogen samples that which are basically the food samples, and we wanted to see the crystallization processes. So we looked into the crystallization processes at three temperatures: 5 degree, 15 degree and 25 degrees centigrade. So if you see in all the curves you will be getting box 1 and box 2. These box 1 and box 2 are nothing but the thermal events that are occurring in the oleogels while it is being characterized, okay, or it is going undergoing crystallization process. So similarly we went for this DSC analysis using the costly equipment, okay, and once we have done that, we went for the this Spearman correlation analysis. So this was the this DSC data and the proposed device data, and we went for the correlation, Spearman correlation analysis. In if you see, except this one, in most of the cases we had a moderate positive correlation, okay. So from here we can say that the device that we have developed, it can provide us information about the thermal events of fat based products, okay. Then as I told you, we went for the analysis of the samples, butter sample and over here also if you see there are two endothermic peaks, and corresponding to these endothermic peaks we got thermal events recorded at this region. So L star versus the temperature, we got this box 1 and box 2 which corresponded with the thermal events that we got in from the DSC thermogram. So this suggests that both the devices again they are capable to analyze the crystallization events in the butter sample. So we expect that it will also be helpful in analyzing these type of crystallization events, say for an example of ice cream or chocolates in the other samples also, okay. So the summary from here is that we were able to successfully develop a dual operating mode system. Okay, so our system, it outperformed the commercial device in terms of the color accuracy. Okay, then we were able to analyze the crystallization kinetics of the oleogels, and the results were somewhat similar with that of the results that we obtain, thermal events that we obtain from the differential scanning calorimeter. Okay, now the problem with this system was we were not able to perform the spectral analysis over here. So that is the main thing. And the second thing is that over here in this first stage we just had a fixed ROI, but in the next stage what we tried to do is that we wanted to uh, include a dynamic ROI selection. The reason being, when we analyze the system, and being a say a material scientist by training, so I always looked into the thing is that when we were characterizing any sample through the imaging technique, we found that our area of interest was at a particular location. Okay, but we were not able to do the analysis. So that training came into my mind, and that expertise came helped us in what you call in nucleating the idea that we need a dynamic ROI region selection, so that we the researchers can determine or capture the data from the specific area of interest. Okay, so the first paper, it was published, and then we had one utility patent and one design patent from these things, from this first chapter. Then we went for the upgradation of the colorimeter to an imaging spectrometer. So what we did is that we had these color spaces, so we had this imaging spectrometer. Okay, now this imaging spectrometer, as I already told you, this is basically an imaging system, and we only have RGB values. So we developed one ANN model, and that ANN model, it was used to convert these RGB values to a spectral value. And correspondingly, what we did is that we also went for the shelf life analysis of the bread samples over a period of time, and we recorded both the RGB values, and the we also performed the microbial analysis and went for the microbial count thing. Okay, then from there, using these two information, we developed a machine learning platform to detect uh, the spoilage in the bread samples. Okay, so we took the samples, then we incubated. Okay, at 37 degrees centigrade, and this is the flow chart. On the right we have the flow chart for the what we did. We first developed this RGB to our reflectance conversion, then through the shelf life analysis we collected this data. Okay, so color and spectral acquisition was also being performed, and lastly we went for the ML modeling. Okay, so this is the setup that we developed, because we are now integrating ML models, so we needed a better computing platform. So we upgraded the system such that it becomes an this computer operated system. So from here we this is the modified software, okay, of the device, and you will get the similar thing. However, what you will get is that herein we are having an additional spectral values. Over here we are not, we did not show all the values because it was getting quite cumbersome. And apart from that, this if you see this color, perceived color, and the color model parameters, whatever we discussed in the first chapter or the first part, they have been shown over here also. Okay, so then, as I told you, we developed a methodology for converting the RGB values into the ANN values. So what we did is that we took Pantone matching system color chart, and we generated 983 color patches, and for these 983 color patches we collected the RGB information through our developed device, and parallelly what we did is that we collected the spectral information from a commercially available spectral sensor. Okay, and from there we developed an ANN model. Okay, so here we developed the ANN model by applying this hyperparameter tuning using random search method. Okay, and once the ANN model was tested, we randomly selected 50 patches from the Munsell color chart. So there are two charts. If you see the Pantone matching system, and we have this Munsell color chart. These two charts or the color chart systems, they are very commonly used in color industry. It may be the paint industry, it may be the food color industry, wherever you go. And we selected separate color charts for training and testing because we didn't want to have a overlap of the color information. Okay, and then from there we collected the reference spectra from the sensor, commercially available sensor, and we went for the this predicted spectra which we developed from the ANN model, and then we use this information and compared it through the Spearman correlation. So from there, we after we were quite confident that our device is working properly and it is generating a good quality spectra, we went for the model deployment and we integrated it to the developed software. Okay, so these are the RGB to reflectance conversion, some results are there, so I am not going into the details of this. So this is the ANN model architecture that we developed and the parameters that we have used. Okay, so this was the ML modeling workflow. So for the spoilage monitoring, okay, so we collected the data, RGB and the spectral data, then we went for the data pre-processing, then we went for the model development and evaluation. For this purpose, we went for the 3 selected supervised learning models and 3 ensemble learning models we have gone, and after training these 6 models we went for the classification purpose. How the data was collected, as I already showed, the bread samples were taken and they were kept in a sterile container, then they were kept at this 30 degree centigrade plus minus 1 degree centigrade, and the readings were taken for 10 days at 48 hours interval, and lastly we went for the color and the spectral data acquisition. Okay, so from here, after the collection of the data, so we went for the feature selection method to reduce the dimensionality of the data, and for that we used the forward selection method. Okay, and for this forward selection method we again use the 6 ML models that we have selected previously. Okay, so from here, after the feature selection, we got that 5 color parameters and 22 spectral parameters. They might be sufficient enough to represent the whole data set. And these 5 and 22 spectral color information we got from the GBT and from the GBT model. Okay, so if you see, GBT model gave 27 parameters, 5 plus 22, whereas XGB parameter, it came up with the same F1 score, but over there we had 48 selected features. Okay, since GBT was having the lower number of the features, so we selected these 27 features for the training and testing. So the data, this was the new data set. Okay, so which were having 27 features, and from there we went for the 2-class distribution. In the 2-class distribution, the samples were classed into fresh and the spoiled, and in the 3-class distribution we went for the fresh, marginally fresh and the spoiled data based on the microbiological data that we obtained. Okay, so then we went for the 5-fold cross validation of the 5-fold cross validation during the training purpose to improve the generalizability, and then we went for the model hyper training and training, and then again the testing and the validation of the results. Okay, so herein this is the sensor data analysis. In all the cases, if we see, we got very strong positive correlation and strong positive correlation among the predicted and the estimated results. Okay, the black line, it is the predicted one, and the red dashed line, these are the standard or the reference spectra that we obtain from the this color these spectral sensors. Okay, so then we collected all this information and all these things. If you see during the spoilage season, over here there has been a significant change in the uh, data, this data as the day progressed. Okay, so this is the shelf life analysis. So this is how we classified the uh, these data sets. D1 means 2 class systems and D2 means 3 class systems. Okay, so this was all based on this microbiological data that we obtained. Okay, so again we distributed the data in this way, and then this is the ML modeling flowchart for the pipelining that we employed. So over here, if you see in the D1, what we were having in the training and the validation, GBT, it gave us the best result. However, if you see in testing, we got SVM as the best result. Okay. Similarly, in D2 also, GBT gave very good results in the training and the testing. However, for the testing, we got SVM as the best model. Okay. So from there we generated the confusion matrix for the testing value. So over here, if you see the SVM, it gave us the best result. Okay. So summary. So we developed a CMOS camera based spectrometer wherein we did not need any what you call spectral lenses or the filters to acquire the data, and inclusion of those systems would have increased the cost of the device. So we were able to get rid of the costly optics that are being employed in the spectrometers. Okay, so this study was published in the journal Food Chemistry with an impact factor of 9.8, and over here again there was a scope for improvement. We can do the image based analysis, and for the image based analysis we can either include deep learning or transformer learning approaches. Okay, so accordingly we did that. We got the data collection. Initially we took the color and the spectral components. Herein we only took the images. Okay, and we employed the 2D CNN and transformer learning models for the estimation purpose. So I am not going into the detail because the methodology basically remains similar. Okay, so I am directly going to the this classification, this thing. So if you see the F1 score for D1 in the testing phase for the for training and validation, it was 99 and 97% for the inception wave 3, but in the testing we got that 2D CNN it performed better. Similarly, in the D2 class where there were 3 class systems, we got 90% accuracy in the testing phase using the 2D CNN that we developed. Okay, so these are the this confusion matrix, and 2D CNN we can see it performed the best. So uh, we have submitted this paper and we are it is under review. So uh, that's it. So where is the scope of improvement? Over here we used only the digital images. Okay, however spectral images, that means the hyperspectral images can be used for this purpose. Okay, so till now what we were having, from RGB we were having we got spectral information. Okay, now say from 400 to 800 we are having this value. Now from where we got this? We selected an ROI, and from there we got the RGB values, and by putting this RGB values we computed this spectra. Okay, now what do you mean by hyperspectral images? Can anyone tell me? No? Okay, So what we have basically in an image, we'll be having a large number of pixels. Now what are these pixels? So I'm not going, so like this it will be there. So what are these pixels? Each pixel, it will be having an RGB data. So can we not convert these RGB pixels for each pixels into the spectral information? Now if you see, if I make some ghost image of different images, say the first one is of say 400, the second one is 450, the third one is 500, and so on. For each pixel, what we are getting? We are getting the spectral values. Now I have to just put in the values. What is the spectral intensity at 400 to the 400 ghost image? Then if I go to the say 450 spectral component, what is the image? In the first ghost pixel for which from which we have computed this spectra, we can put in this value in the second image. Similarly, if we go for the 500 wavelength, nanometer wavelength, we will be getting an intensity, and that intensity can be plotted over here. So if we go for each of the pixels, measurement for each of the pixels, you will be getting the hyperspectral images. You will be getting an images for 400 nanometer, for 450 nanometer, for 500 nanometer, and that way, right? So in this way, when you are doing this, so you are creating images that are of different wavelengths using a single RGB image, okay. So that means using any CMOS camera or any color camera, you will be able to generate hyperspectral images in the visible range, okay. So that was our funda, and based on that we went for the upgradation of the spectrometer into a hyperspectral imaging system, and this is what it has been given. So we use that 2D CNN and the inception model and the other this transform learning models for the classification, but instead of just using the image, normal image, color image, we used the hyperspectral images, okay. And in the first case, if you see, we try to find out in the spectrometer case, we try to find out the what are the wavelengths, okay. In this case, we perform the wavelength selection using two methods. One is manual method, wherein by looking into the spectra, we just identified the important spectra, this wavelength points, and we used it. And in the second one, we used an automatic method. We used this model selection methods to calculate this spectral, to find out the spectral values which can give us very good results, okay. And the rest of the things, data acquisition, it remains similar, okay. So this was the modified thing where we get the hyperspectral info. We can get the spectral images also from there, and from there we can also generate the hypercube, okay. So this is what I try to make you understand, okay, the spectral images. So data collection, I already told you it was similar. So I am directly going into the results again. Yeah, feature selection, here the feature selection, it was the forward selection method we have used, okay. And uh, we have used the spectral information over here for the yeah, auto wavelength selection, okay. So from there we selected this manually selected wavelengths and the auto selected wavelengths, its data it is given over here, okay. So these are the spectral thing. So from here, if you see how we selected the data points, it's there. This is the model, this manual method. Then over here we went for this generation of the hyperspectral images at this manually selected wavelengths and auto selected wavelengths, right? Then we have this data set uh, distribution. Okay, so let's go for the accuracy. In the accuracy, if you see in the testing, we have ResNet 50 as the better model, and in the D2 this thing we had this Inception V3 as the best model. Okay, so ResNet 50 for the D1 class and Inception V3 for the predicted class, for the D2 class dataset. Okay. Similarly, for the this auto wavelength selection, we get 2D CNN and Inception V3 for D1 and D2 respectively. Okay. So these are the key findings. So we are in the process of communicating this for the project for the publication, and we expect that that in the couple of weeks time we should be able to submit this project, submit the paper to the to the journal. Okay. So real time, then we went for the real time testing. So this is what it looks like before testing. So herein we have basically developed an unified software, and we tried we integrated the best performing ML and the DL model. And after testing, if you see the prediction panel, it will give you in the D1 class, as for the D1 class, whether you are having the fresh or spoiled. Similarly in D2, whether you are having it as fresh or spoiled. From the normal images, again the D1 image it says spoiled, whereas D2 image it says likely spoiled. And the hyperspectral images, we are having D1 and D2 fresh and likely spoiled. Okay, so in this way we, and these are the classification testing classification results. Okay, so overall conclusion, we were able to develop a multimode colorimeter cum spectrometer cum snapshot hyperspectral imaging system. We were able to develop some machine learning models that can be integrated with the device, and these low cost devices, they can be used for what you call for the spoilage monitoring purpose. Okay, shortcomings, uh, limited ANN color training because of the limitation of the color chart. We can, in future we can increase the color training database. Then over here we just used BRED as the validation model. So we had a restricted food system validation because within 5 years you can do a minimal amount of thing. So then we have only done the lab level validation, and the CMOS sensor that we have used, it is just a 5 megapixel camera. So if we increase the camera size, we may go for we may get better results in future. And lastly, poor model interpretability. Some people may find it very difficult to interpret the results if proper training are not given. So we are working on that, how we can reduce the interpretability of the results. So the in-house developed this computer control spectrophotometer. It would cost somewhere around 20,000. If you want to try to develop the spectrophotometer in the standalone mode, it can cost around 60,000. And in-house developed spectrophotometer come hyperspectral imaging system, it would cost you around 80 to 1 lakh rupees. Okay, for the developmental purpose. So uh, in this way we can see that by uh, understanding some basic phenomenon, we will be able to develop some systems that can be used in our labs. Okay, so these are some of our notable collaborators. Okay, so some of our notable international collaborators are here. Okay, so this is our YouTube channel. We post about our research, what we are doing in our lab over here. So thank you very much. If you have any question, we'll be happy to, I will be happy to answer those.
Gaurav sir.
Yes, I have given
Access.
To all the participant, they can unmute themselves.
हाँ.
Yes.
हेलो।
यस सर,
हाँ सर, नमस्कार सर।
नमस्ते।
सर नाइस लेक्चर। सर मैं एक चीज समझ नहीं सका कि आप क्रिस्टलिनिटी देख रहे थे बटर में एंड ऑयल्स में ऑल्सो। वहाँ एक स्लाइड है जहाँ पे आपने इनिशियली दिखाया सनफ्लावर या राइस ब्रान ऑयल के बारे में।
हाँ जी, हाँ जी।
तो मैं सर एक चीज नहीं समझ सक रहा हूँ, वहाँ पे आप एक्चुअली देख क्या रहे हैं। जैसे कि हमने मार्केट से एक तेल खरीद के लाया, तो उसमें अगर एक तेल एक्सपायर डेट है और एक विदाउट एक्सपायर्ड है, तो हम तो खाली हमें तो कुछ समझ में नहीं आएगा। तो इसके लिए ये मशीन है कि ये मशीन हमें बता देगा कि ये एक्सपायर्ड के बाद क्या हो रहा है क्या नहीं हो रहा है। तो ये जो आपने समझाया हमें, इतने साइंटिफिक आपका फील्ड फूड केमिस्ट्री में जितने सारे इंस्ट्रूमेंट एंड दैट डाटा, एक्चुअली नॉर्मल में अगर समझ में चाहे तो वो कैसे समझे सर, थोड़ा बताएंगे प्लीज।
हाँ, हाँ, देखिए, यहाँ पे क्या हो रहा है, मैं फिर से आपको शेयर करता हूँ स्क्रीन।
हाँ प्लीज सर, प्लीज।
यहाँ पे जो हम ये बोले हैं, यहाँ पे देखिए राइस ब्रान ऑयल, कैंडिलिला वैक्स एंड सनफ्लावर लेसिथिन से हमने एक ओलियो जेल बनाया। ओलियो जेल क्या है? ओलियो जेल है जैसे आपका ऑइंटमेंट देखे होंगे, बटर देखे
या
होंगे या फिर घी देखे होंगे। तो घी में
हाँ
क्या
हाँ
हो रहा है, आप अगर उसको हीट करते हैं तो हीट करने से वो ट्रांसपेरेंट हो जाता है, राइट?
या
जब आप उसको
यस सर,
कूल करना शुरू करते हैं, वो फिर पहले आपका वो
सॉलिडिफाई हो
क्लाउडी
जाता है।
सोल्यूशन होता है, ठीक है?
या
फिर वो
या
क्लाउडीनेस बढ़ता बढ़ता जाता है। उसमें क्या हो रहा है, उसमें जो हो रहा है, जो सॉलिड फैट्स हैं, सॉलिड फैट्स वो आपका प्रेसिपिटेट आउट हो रहे हैं सोल्यूशन फॉर्म से, एंड देन वो सॉलिड फैट्स वो नेटवर्क फॉर्म करके एक सॉलिड स्ट्रक्चर बना रहा है, राइट?
या
द ओलियो जेल्स, इसमें क्या है, यहाँ पे ये ओलियो जेल्स इनको कंसिडर किया जाता है कि ये ओलियो जेल्स आर बेटर ऑल्टरनेटिव टू द बटर और द घी, क्योंकि घी और बटर में आपका सैचुरेटेड फैट है। तो इसलिए लोग क्या
ओके
ये कर रहे हैं, दे आर गोइंग टूवर्ड्स द बटर और घी ऑल्टरनेटिव। और यहाँ पे आप अगर देखेंगे, इसमें कैंडिलेला वैक्स जो है, जो सैचुरेटेड फैट है, इट इज ओनली 5%, बट इन बटर एंड घी
ओके
इट इज अराउंड 70 to 80%, ठीक है? लेकिन इसमें क्या ये है, प्रॉब्लम क्या है, आप इतना कम सैचुरेटेड फैट से आप इसको बना रहे हैं, तो इसका प्रॉपर्टी तो अलग हो जाएगा
यस
ये बटर और घी से। और हमारे
यस
मुंह में देखिए, अगर आप नॉर्मल तेल आपके जल्स आपके टंग में लेंगे, उसका कोई टेस्ट नहीं है।
नहीं है या
टेस्ट किसका आता है? टेस्ट आता है, ये सॉलिड फैट जब ये होता है, मेल्ट होता है, वो हमें एक फीलिंग देता है, ओके?
या
वो हमें एक
हाँ
फीलिंग देता है, और हम उसको बोलते हैं टेक्सचर, ओके? इन
यस
फूड साइंस में हम उसको बोलते हैं टेक्सचर। वो
ओके
टेक्सचर से ये करके आप एक आइसक्रीम को पसंद कर भी सकते हैं, नहीं भी कर सकते, ये कोई फैट बेस्ड सिस्टम को पसंद कर सकते हैं, नहीं कर सकते। एक मैं आपको सिंपल एग्जांपल दूंगा। इसका एक कॉमन
यस सर
एग्जांपल है आपका, जो फ्रोजन डेजर्ट्स आता है और अमूल का जो ये आता है। अगर आप फ्रोजन डेजर्ट किसी लोकल कंपनी से खरीदेंगे, उसमें आप देखेंगे कि उसका टेस्ट आपको अच्छा नहीं लग रहा है, लेकिन इंग्रेडिएंट तो सब सेम है ना? इसका मतलब है जो
या
फैट जो क्रिस्टलाइज किया है वहां पे, वो ठीक ढंग से नहीं किया होगा, क्योंकि प्रिपरेशन कंडीशन में वो प्रिपरेशन कंडीशन ठीक से मेंटेन नहीं किया गया होगा, ओके?
या
लेकिन फ्रोजन डेजर्ट अगर आप ये क्रीम बेल का लेंगे और अमूल का लेंगे, क्रीम बेल भी एक अच्छा कंपनी है, अमूल भी एक अच्छा कंपनी है, दोनों का लेके आप टेस्ट करेंगे, आपको वो पता नहीं चलेगा। अमूल इज फुल क्रीम, उसको आइसक्रीम बोलते हैं, फ्रोजन डेजर्ट नहीं बोलते हैं, राइट? इसको लेके बीच में आपका काफी हंगामा भी हुआ था, 1-1.5 साल 2 साल पहले। अमूल ने उनके ऊपर केस किया था, बाकी सब आइसक्रीम मैन्युफैक्चरर्स के ऊपर, कि आप उसको आइसक्रीम नहीं बोल सकते क्योंकि आप उसमें क्रीम नहीं डाल रहे हो, विच इज बेसिकली सैचुरेटेड फैट, जिसमें सैचुरेटेड फैट है। तो इसमें आप क्यों नहीं कर पा रहे हो? इसमें आप क्यों इसलिए नहीं कर पा रहे हो कि फ्रोजन डेजर्ट में आप ये क्रीम का ऑल्टरनेटिव डाल रहे हो, लेकिन वो एक टेक्सचर दे रहा है विच इज सिमिलर टू द क्रीम, एंड ड्यू टू दैट रीजन दोनों का जो आप फ्रोजन डेजर्ट और आइसक्रीम खाएंगे आपको उसमें फर्क नहीं पता चलेगा। तो हम लोग एज ए फूड साइंटिस्ट जब हम उसे एनालाइज करना चाहते हैं तो उसमें उसका क्रिस्टलाइजेशन कैसे हुआ नहीं हुआ वो कैसे पता लगाएंगे। वो हम लोग फिर इस मेथड से जाते हैं कि जैसे यहाँ पे देखिए हमारा टेम्परेचर है और एल स्टार वैल्यू वो एक कलर पैरामीटर है। हम उसको जब कूलिंग कर रहे हैं वो किस हिसाब से वो आपका क्रिस्टलाइज कर रहा है और उसका ये जो पैरामीटर जो है ये जो प्रोफाइल जो है वो कैसा बन रहा है उसके ऊपर हमारा वो टेक्सचर बनेगा। समझ में आया आपको?
यस सर, बहुत बढ़िया से आपने समझाया।
हाँ
सर
ठीक।
मगर मेरा ये क्वेरी है कि जब एक बटर, तो वो बटर विथ
आपका वॉइस ब्रेक हो जा रहा है।
एक्सपायरी डेट की बात होता क्या है?
एक्सपायरी डेट के बाद होता क्या है वो आपका
हाँ,
ऑक्सीडेशन
दोनों में
होता रहता
अंतर
है।
क्या है? तो ये नहीं नहीं, मैं क्या बोल रहा हूँ, देखिए सर, उसको हमने फ्रिज में रखा, राइट?
हाँ।
उसको हमने फ्रिज में रखा
हम्म।
और उन्होंने एक एक्सपायरी डेट डाल दिया है कि ये इतने में एक्सपायर्ड हो जाएगा। एग्जैक्टली सर, ये
हम्म।
प्रैक्टिकली मैं आपसे पूछ रहा हूँ। हाँ, मुझे ये जानना है एक्चुअली कि आप काम करते हैं इस एरिया में, तो ये बहुत आई फील सबके लिए इंपॉर्टेंट होगा कि एक फूड आइटम है जो बटर है, बटर का एक एक्सपायरी डेट है और हमने फ्रिज में रखा, अगर नहीं खा रहे हैं वो एक्सपायर्ड हो गया,
हम्म।
तो एक फेस अगर लाएंगे और उस एक्सपर्ट के साथ कंपेयर करेंगे तो हमें क्या डिफरेंस मिलेगा? उसमें क्या माइक्रोबियल ग्रोथ हो जाता है, या जो जो उसमें फैटी एसिड्स है, राइट, जो एसेंशियल और जो है वो टूट ब्रेक डाउन हो जाता है, या क्या होता है? क्योंकि हमने तो उसको कंडीशन मेंटेन करके रखा है। एग्जैक्टली, यू अंडरस्टैंड नो सर?
हाँ नहीं नहीं
होगा
वो
क्या?
सही बात है। आप
क्या
आप
होगा एक्चुअली? आपने कभी ऐसे काम किया है सर? उसमें स्टडी किया है क्या? आप करते होंगे तो मैं इसीलिए पूछ रहा
देखिए
हूँ, प्लीज सर।
जैसे आप तेल के बारे में बोल रहे हैं। तेल में पानी नहीं है ज्यादा, उसमें है ही नहीं पानी।
या
ब्रेड में क्या है
यस
आपका
सर।
पानी है इसलिए आपका माइक्रो ग्रो कर सकता है। तेल में क्या है, तेल में आपका है फैटी एसिड्स है। कुछ सैचुरेटेड
हाँ,
फैटी एसिड्स है कुछ अनसैचुरेटेड फैटी एसिड्स है।
अनसैचुरेटेड फैटी एसिड्स है,
एंड
यस।
अनसैचुरेटेड फैटी एसिड का क्या हो सकता है, ऑक्सीडेशन हो सकता है। क्लास 11 12 का बेसिक जो नॉलेज है हम लोगों के
हाँ
पास,
सर,
एंड
यस सर,
सैचुरेशन है तो उसमें ऑक्सीडेशन प्रोन है। तो
यस
ऑक्सीडेशन
सर।
प्रोन है तो वो जब आप रखते हैं आप जितना भी
हम्म,
स्टेबलाइजर लगाइए कुछ भी लगाइए वो धीरे धीरे ऑक्सीडेशन तो होता रहेगा। तो धीरे धीरे
ओके,
एक्सपायरी के बाद उसका ऑक्सीडेशन हो जाता है प्रीडोमिनेटली तेल में।
अच्छा।
ठीक।
अच्छा, आई मीन टू से कि नहीं सर, आपने कभी ये ऐसे अगर काम अगर प्रेजेंट करें ना, बहुत बढ़िया लगेगा सर।
हमने
रिक्वेस्ट
नहीं किया
करते हैं कि ऐसे
ये सब बेसिक चीजें हैं जो कि आपका काम ऑलरेडी हुआ पड़ा हुआ है।
ओके ओके
अच्छा,
ओके
हाँ
ओके
हाँ
ओके,
हाँ।
हमने
हाँ
तो
आप
एरिया नहीं है
नया
ना सर,
नया
हमें ये
पर्सपेक्टिव
एक्चुअली।
आप दे सकते हैं। आप जो बोल रहे हैं वो भी सही
हाँ,
बात है तो
या
वो कर सकते हैं
क्योंकि
लेकिन
सर,
हाँ
क्योंकि सर
लेकिन
देखिए
उससे
ब्रेड
फिर
जो
वो
होता है ना,
पीएचडी का थीसिस नहीं निकलेगा ना।
ना ना, नो नो सर, ठीक है।
हाँ
सर जो ब्रेड है ना,
हाँ
ब्रेड
जी।
एक्सपायर डेट के बाद भी एक दो दिन के बाद भी आदमी फ्रिज में रख के खाता है।
हाँ आपका ब्रेड
इफ यू
का
सी
कितना दिन का
खाता है।
आता है ये हमने तो कमर्शियल ब्रेड लेके किया है। आपका
हाँ
ब्रेड का जो एक्सपायरी डेट आता है 5 दिन का मैक्सिमम रहता है।
हाँ,
हमारे यहाँ से
रहता
देखिए
है,
वो
यस सर।
6 दिन के बाद से वो न- मतलब अर्ली स्पॉइलेज का ये दिखा रहा है, साइन दिखा रहा है
दिखा रहा है, यस। हाँ।
अर्ली स्पॉइलेज का। तो आप
हम्म,
मतलब जब माइक्रोबियल काउंट कम है
हम्म।
तब भी आप खाना खा सकते हैं। मैं आपको एक अच्छा एग्जांपल दूंगा। आप नॉर्थ इंडिया से है क्या?
नहीं सर, आपका उड़ीसा से हूँ
उड़ीसा
सर
से,
मैं।
अच्छा ठीक है।
राहुल कल, हाँ।
हाँ ठीक है। तो आप जब दही बनाते हैं
हाँ,
गर्मी के दिन में, अगर आप दही को अगर 2 3 दिन एक्स्ट्रा रख दोगे तो क्या होगा?
या ये सर अंडरस्टैंडिंग, या स्मेल करता है और ग्रोथ ज्यादा हो
बहुत ज्यादा
जाता है सर
खट्टा हो
उसका।
जाता है ना?
हाँ हाँ
तो
सर,
वो
हाँ।
उसमें वो क्यों होता है?
दैट इज
वो
बैड फॉर,
क्योंकि माइक्रोबियल काउंट जो है वो बढ़ता रहता
बहुत
है।
हो जाता है, या
हाँ हाँ।
हाँ।
लेकिन दही में भी तो माइक्रोब है, लेकिन
यस
हम लोग उसको
यस,
तब तक ले सकते हैं जब तक वो आपका
अप टू लिमिट।
विद इन द
या
लिमिट है। कंजम्पशन लिमिट के
या
अंदर जब तक है तब तक हम
हाँ।
उसको ले सकते हैं। वो कंजम्पशन लिमिट से बाहर चला जाएगा तो वी कैनॉट टेक इट।
ओके सर, थैंक यू, बहुत बढ़िया लगा सर आपसे बात करके,
या
थैंक यू।
थैंक यू।
So actually we
Okay.
are getting late, sir.
Yes.
So sir, it was truly. Give me a moment, sir. Rakshi sir.
Yeah. Thank you, Professor Pal, for your insightful talk on the development of biosensing devices. And it's always a pleasure to listen to a fellow Jadavpurian working in this field and doing such fantastic work. It was a pleasure to have you with us today.
Thank
And
you,
I want to invite Dr. Rivnesh to present this memento to Professor Kunal Pal. Please, Dr. Rivnesh.
Sir, it was a great honor to have you as a keynote speaker for our faculty development program. We sincerely appreciate your time, insight, and experience you shared with us. Sir, please accept this memento as a token of our deepest gratitude and appreciation. So it was truly an honor, sir, to have you here.
yeah, thank you, thank you.
Okay.
Yeah.